So today we're going to finish the one-dimensional particle in a box simulation. So we've done the particle in a box energy calculation and the transition dipole moment, the intensity of a spectral transition by hand in Calculus Week. We did it by symmetry using odd and even functions, and that was super easy. We did it on a cocktail napkin, okay, just to kind of prove the point that it can take, what was it, 16, 13, no, yours was 16 pages of math and reduce it to a 6 by 6 inch square. And then now we're talking about numerical methods where we do this in a spreadsheet. You don't have to use a spreadsheet. I like to use a spreadsheet for two reasons. One, it's very visual. When you have a function, you have the x-axis going down in the rows, and then you see the y column, the wave function. You can plot that. You can see that it looks like a guitar string and so on. It's not the fastest, but it's fast enough for us. Okay. If you wanted to do this faster for larger molecules, bigger systems, you'd probably go to something in the past they used was Fortran, formula translation. It was a computational language, and they wrote Gaussian, this computational chemistry package called Gaussian in Fortran, and they still use Fortran today in Gaussian. They haven't converted the code over to C or one of the newer languages. So we're going to learn about the simulation process. So just like we've had these schemes in the past, this is the scheme for simulating a spectrum. So some of this is review. So a lot of this morning you can kind of relax and just let me sweep back over material that I've already covered. Okay? That's sort of the way I teach. I don't just give it to you once. I give it to you once, and then I come back and give it to you again and push it forward further. And then I come back and give it to you again and push it forward further. So if you feel like it's review, that's fine. It should be review, but then you'll get something new right after that. Okay, so try to stay alert. Don't just say, oh, I've heard this before, and kind of shut down. Say, I've heard this before, but where's he leading with this? Because he's going to go past where I've been and go a little bit further to stuff I don't know. So we've had the Schrodinger equation, and from that we turn the wave functions into an energy equation. And pretty much now, and you need to write this down, okay, you should have that energy equation for a particle in a box memorized. Like, you should be able to write that out. We've used it so much, you should be able to just knock that out. So let's just practice. Let's say the energy for a particle in a box. So a one-dimensional particle in a box. Let's try to figure out as a class what's in that energy equation. So just give me one piece. Don't give me the whole thing so we can do this as a class. So you have a piece to give? What? N. Okay, is it N by itself? Is it N squared, N plus 1? N squared. Okay, someone else? Planck's constant. Okay, yeah, top and bottom. Top or bottom? Top. Squared. Very good. Something for the denominator. 8. 8. Okay, very good. Nice. Next. Pi. Well, pi was in there. Okay, but it got canceled. So it was h bar, which was h over 2 pi. And then when we did the second derivative, the n pi x inside the sine function came out twice, so we had a pi squared on top. And so it was h bar squared, which gave us 2 squared and pi squared. But then after we did the second derivative, pi came out twice, and it was pi squared on top, so it canceled. But it was originally in the Hamiltonian. Okay. M. Okay. Top or bottom? Bottom. Okay, the m's not squared? No. Correct. Okay. L squared. So that's it. That's the particle in a box energy equation. We got that from the Schrodinger equation and the wave functions. Okay. So then let's go back to. So then we sort of set that aside for a second. And we looked at the transition moment integrals. Now that was the wave function perturbed by light. So x was used to represent light as an electric field. Okay, so we had x times psi, and then we multiplied that again by the wave function, the upper wave function, or where it was going. And so we had psi x psi. That was the transition moment integral. We integrated that over all space, and that gave us the intensities for absorption or emission. It was a probability of that transition. Now, if we had done x squared, we would have gotten a Raman or Rayleigh scattering selection rules. So from the transition moment integrals, if we did the actual integrals, we would get the intensities. Okay. If we just looked at the symmetries of those, we could get zeros and non-zeros. And so we could get the selection rules from those. So the non-zero results of this integral were the selection rules. And then we use the selection rules to come up with the transition equation. So in the spectrum, the x-axis, where the peaks show up, that is actually the differences in the energy levels. And those differences are calculated using the transition equation. So we then set that aside, and we calculated the thermal population of those energy levels. That's the Boltzmann distribution. And so if we multiplied the thermal population times those transition moment integrals, we get what we call a stick spectrum. So we just have sticks. We say at this wavelength is a transition, and what's the height of that transition? How strong is it? And so we could just plot sticks. Okay. And then today, the new stuff is the line shape formulas. So we've gone all the way to the stick spectrum in the past. Now today we're adding on this new material called the line shape, where we actually take the shape of the transition. When I get close to that stick, there's a chance that molecule or a certain portion of those molecules can start absorbing, just because you're close enough, right? And so that stick is not infinitely tall and very narrow. It's actually spread out a little bit. What's the shape of that spread? That's the line shape. Okay. So the Schrodinger equation, I'll just review these things. So we had the wave functions. We had the Schrodinger equation with the wave functions in there, and that second derivative operator. This is something important in our numerical calculations. How do we calculate the derivative? It's just rise over run, correct? Mm-hmm. So that's pretty easy, delta y over delta x. But after you calculate delta y over delta x, where do you put that result? This is an important thing that can screw up our calculation a little bit. So focus on what we've got here. We've got 3 data points. And so in our derivative, we've got 3 data points, and I could calculate the differences. If I just take this data point and calculate the next data point and take the difference, that's called forward slope. Okay? I'm standing on a data point, and I'm looking at the next data point, and I'm saying, okay, the next y minus my y divided by the next x minus my x. And so notice I'm looking forward. What happens if I put that slope on the data point I'm standing on? Okay, it's a little off, isn't it? Because look here, the slope of that curve is 0 right there at 0. But if I calculate the forward derivative, I get a negative value for the slope where it's not negative. That's a problem, especially for symmetry. If we want zeros to show up where they're supposed to be, things to cancel out the way they're supposed to cancel out, forward derivatives are going to give us an error. Okay? And so you're actually putting a negative slope right here at 0 where it's not negative. The slope there is 0. Or we could look behind us. We could say, what was the last data point? I could take my current y and subtract the previous y, and current x and subtract the previous x, take that ratio and I would get a positive slope. But still, if I plot that right where I'm standing, and I'm standing at a 0 slope space, then I'm getting an error. So that's why in our spreadsheet we did the center derivatives, the centered slope. I took the data point, next data point, and subtracted the previous data point. And if you look at that, wherever there's a critical point in the curve, a maximum or a minimum, then the slope is accurately calculated as 0. So that's why we did this center derivative calculation in our numerical derivatives, is so that we could get an accurate placement of our critical points where things went to 0. And so that was important for maintaining symmetry. And so right there where this curve has got a 0 slope, since we're calculating the centered slope, then it goes 0. Also, notice that if I do the previous data point and calculate the derivative, I've got to have a data point that goes beyond the end of the box. See here, if I'm going to calculate the slope at that point there, I need a previous data point to use to calculate it. Okay? Or if I if I go past, if I'm trying to calculate the slope over here, I need a data point beyond the box so I can use the calculate. And same thing if I'm using centered derivatives. I need an extra data point on either side to calculate the slope. What if I have to then calculate the second derivative? I need another one. So that's why we went beyond the box at the top and bottom of our wave functions 2 rows. Because we had to calculate the slope twice. And every time we calculate the slope, we lose a data point. So if we're going to take 2 derivatives, we need 2 rows on top and bottom if we're doing the center derivatives. If I'm just doing forward derivatives, I only need 2 rows at the bottom. If I'm using previous or reverse derivatives, I just need 2 rows at the top. But because I'm using center derivatives, I need 2 rows, 2 at the top and 2 at the bottom. Because every time I take a slope, I use that extra data point and then plot the difference where I'm standing. And so that data point goes away. And so you can kind of see that here we've got the extra 2 rows up here. That's these 2 rows here. In this particular example, my box length is 7, so I go from minus 3.5, which is L over 2. So that's minus L over 2. And so you see the 2 rows previous to that. And so let's take the first derivative. Notice one of those rows is now blank. Okay? So it went away. Once I calculated that difference, then I don't have a difference for that first row. And so it doesn't have a result. And also notice the plot. We've got the derivative of a sine function is a cosine function, and these are cosine functions times dx, whatever came out of the middle. Okay? And now we have psi double prime, or the second derivative of our wave function, and now those 2 extra rows are empty. So it took those 2 extra rows to calculate our second derivatives. And we see that now it's also, the third derivative of cosine is minus sine, and you see these are minus signs. They start going negative instead of going positive. Okay. So then we take that, we've got that psi double prime, which was the second derivative here. And we use, like we discussed last time, a transpose of that psi matrix, which was a 15 by 100 matrix. We flip it sideways, and we use matrix multiplication, M-mult, to multiply by psi double prime, and we end up with our energies. Okay. So this is what you're doing in the spreadsheet for the Schrodinger equation. Transpose of that psi times psi double prime, and then you end up with the energies. And then you also have to include the constants that came out front. So, and you have to include dx. So once you include all those extra constants, then you end up with the energies. And they should match the energies calculated from this equation. One of your discussion questions, though, is to look at the errors. They don't match it exactly. And it does get worse with higher quantum number. And so that's one of the questions that I ask. So whenever you're dealing with numerical analysis, there's errors based upon how small you chop your wave function. And so if we had 100 rows, we'd get a certain amount of error. But what if we had 1,000 rows? We'd be chopping it in tinier spots. What happens if we have infinitesimal x's? Then you get the analytical result. So you just don't have spreadsheets that big to make x infinitesimal. So there's our energies. What's nice about matrix multiplication is you can do all of those integrals at once, 225 integrals. Most of them are 0 because this is only a wave function times its own second derivative. A wave function times any other second derivative gives you 0. So that orthogonality shows up also in the energy matrix. So the energies are the diagonals in that integral. And so you can just walk down and see the energies for each of the quantum states. Next, we did the transition moment integral. And so we had that x perturbed wave function. So x times psi is shown here. And now we're ready to do that matrix multiplication. So again, transpose the wave functions, multiply them by x psi, and integrate over all space using M-mult. So again, we have that 15 by 100 matrix. So now it's psi times x psi. It's the transpose of psi times x psi. And using matrix multiplication, you get the sum of those columns. And so this gives us the intensity for absorbance in this case, because we're just using x. If it was x squared, it would be scattering. Okay. And we get the intensity of those absorbance transitions for each n going to n prime. So transitions between n. And we see this selection rule. So you see this pattern emerge where the non-zero cells are at odd jumps. So n going up by 1, 3, 5, 7, etc. We can use that now to come up with the transition equation. If we know that it's non-zero for delta n equals 1 and delta n equals 3 and 5 and so on, then we can take this energy equation and calculate those differences to come up with the transition equation. So we've done this, you've seen this slide 3 times now. Okay, so you should see the algebra involved, and there's the delta n equals plus 3. And so then we do the Boltzmann distribution. So this is the thermal population of those levels. This is where the temperature dependence of the spectrum comes in. So if I have a high temperature, with lots of excitation thermally, and so then we can have the 5 to 6 transition. Whereas if it's cold, we only get the fundamental, which is the 1 to 2 transition. So we start to set up the spreadsheet where we do these things horizontally. So across the top, you have just peak number, just a generic labeling of the peaks. Then we have the selection rule, delta n equals 1. So this block here is just going to have the delta n equals 1 transitions. Further down to the right, you'll have the delta n equals 3 transitions. And then if you wanted to, the 5s, but they're really, the intensity is going to be so small, you won't see them. Then we have just I go ahead, instead of using the transition equation, I just put in the quantum numbers, 1, 2, 3, 4, 5, all the way up to 15, and then, or to 14, and then 2, 3, 4, 5, all the way up to 15. You can't go from 15 to 16 because we didn't calculate 16. So you can calculate those, and then I just have that energy equation input in to calculate the energies of these different quantum states. So here's the energy for n, here's the energy for n prime, and here's the delta E. Okay. And then I convert that delta E into wavelength using Planck's equation. So equals h nu, and what's nu? C over lambda, and so then we calculate lambda. So those are our wavelengths for the transitions. Now then I have a Boltzmann factor rho, and it's just this equation. Now for all of our transitions, for the particle in a box, Gn is equal to 1. Okay, so these are all singly degenerate. When we get to rotational transitions, it's 2j plus 1. So whatever quantum state you're in, if you're in j equals 3, then the degeneracy is 2j plus 1. So it'd be 2 times 3 is 6, plus 1 is 7. So the degeneracy for j equals 3 would be 7. And so whatever thermal population you had for that energy level would then be multiplied by 7, because essentially there's 7 chairs. And if you're throwing molecules in there thermally, there's 7 places to sit. And so that's 7 times the probability that you could have a molecule in j equals 3 than there would be in j equals 0. Okay. So then we have the energy of the initial state. So this En is this energy right here. And then Kt. So K is Boltzmann's constant, and T is the temperature on the front page. And so for our calculation here, it's 500,000 Kelvin, just because we wanted some excitation for those electrons. Okay? So that's the Boltzmann factor. You see that they start at, for the ground state, 1, and then just get smaller and smaller and smaller. Okay. They can go up bigger if the degeneracy grows. And so for rotational levels, the degeneracy gets higher, and so you have a Boltzmann factor that goes up for a little bit and then comes back down. Because it goes up because of degeneracy, but then goes down because of temperature. And then if you combine these, you have the stick intensity. So the intensity of the stick would be the Boltzmann factor times that transition dipole moment integral. And you could plot this now. This would give you the stick spectrum. So we have the individual intensities, the Boltzmann factor times the transition dipole moment. And you can plot that versus energy and get the stick spectrum. So here's the energy stick spectrum. And you've seen this one before as well. You see the 1 to 2 transition, the 2 to 3, and so on. Okay. So let's see if we can figure out, just for review, What is this one called? 1 to 4. Yay, overtone. What is, let's be silly here, and what is this one? It's an overtone hot band. Yeah, okay. And this one here, 5 to 6. That's just a hot band. Yeah. Where's the fundamental? Yay, 1 to 2. Okay, great. This is so easy for me to ask. You know that I'm going to put a big old stinking plot right there on the exam and ask you all kinds of questions about it. But I'm happy because I hear lots of people saying, oh, yeah, this is easy. Okay. So we have that stick spectrum, but I could plot it also versus wavelength, and I would get this sort of inverse distribution of the peaks. And so then there's the wavelength spectrum. And then finally we come to the new material for today, the line shape functions. There are lots of things that can impact whether an atom or molecule will absorb light. And although this material is not in the PowerPoint, I didn't really have time to draw all these kinds of fancy, I'd say fancy pictures of moving molecules. But let's just, let's see, let's not do that. How do I escape? Well, I didn't want to kill it actually. All right, let's go back to this. Okay, so let's say in our spectrum we have a transition here, and we're scanning the light with our monochromator from long wavelength to shorter wavelength. And so our monochromator, so the light's coming off of our source, bouncing off a mirror, going through some slits. When you take instrumental, you'll understand what's going on here. So the light hits this and comes off in a rainbow. Yeah, you could use a prism as well. Where'd all my colors go? Look at that, I got all black. Red. And so let's say our transition is actually orange. Yeah, exactly. So when we get to orange, we're going to have the strongest probability of absorbing light. But we're right here, we're approaching red. Okay. So there's no peak at red. Let's put a red dot there. And so then our monochromator is turned now to we're sending red light through our sample. And I'll show you just one mechanism for broadening of that line. Here's my little molecule in my cuvette. And it's moving towards the light. So what light do you think that molecule experiences? It's red light hitting it, okay? But the wave's coming at the molecule like this, and the molecule is coming at the wave. So it's experiencing the wave at a higher frequency, right? And to that molecule, that light looks orange. And so it absorbs it. But we're not at orange yet, but it absorbs it. And so we're getting some signal already. We're not at orange yet, but we're getting some signal. And this happens a lot, okay? And it happens smoothly. And so we get some signal here. We get the most signal at orange, but we start getting some signal here. Do you see how this works? It's not perfect. We don't have to wait until we get exactly at orange for the molecules to absorb. We have motion, in the molecules that can cause this red photon to be appearing to the molecule as orange. And so it's going at the right frequency and it can absorb. Okay. You also have the energy level differences in the molecule. Well, you might have some molecules that are in the midst of a collision right when that photon hits. And so the molecule hits another molecule and its energy levels are moved around just to the right spot where the red light absorbs. Okay? And so there might be a few molecules here that are able to absorb that light just because they got collided with right then. And so that would be called collisional broadening. Okay? These are advanced terms. I'm not really going to test you on this, but it's good to write down if you're interested in it. Okay? Collisional broadening can cause the line shape to broaden out. So molecules are in the midst of a collision right when that photon hits it. And the photon is what we call detuned a little bit. It's not right on the transition. So if you had a molecule isolated in space, no collisions, no velocity, no other external fields, this would be the transition location. It'd be at orange. Okay? But if you've got a molecule that's moving, colliding, okay, under pressure, then this might be the absorption center for a few of those molecules. If you add up all of these effects and it's random, so if it's just a random smearing of that line, what is the line shape function for random distribution or random errors? What? No? So when we talk about random fluctuations or random cause uncertainty, what's the distribution function for that? Anybody know? Anybody hear this? Anybody take a statistics course? Okay, fantastic. All right. It's the normal distribution because it's normal uncertainty. Okay? And the normal distribution is the Gaussian distribution. That's why that functions in Excel, because it's used so much for random uncertainties or normal uncertainties. It's the Gaussian distribution function or the normal distribution function. And so that's what we would see for collisional broadening or something of that sort. And so this Gaussian line shape is the normal distribution function. Now, it's slightly different than what you would see in a statistics book because this is written for spectroscopy. It's been modified a little bit. It's the same function, but instead of using sigma, which would be the standard deviation, the sigma is the distance from the middle to the inflection point on the curve. And that's not the full width at half maximum. So typically in spectroscopy, we come down from the maximum halfway, and we talk about the width of the peak. So the full width at half maximum, that actually should be a vocabulary word. I didn't write that on the week 5 vocabulary, so write this down. I was coming up with them really quickly this morning. So
line width at half maximum.
Full width at half maximum. So let's go back to 5 here. So FWHM, that's the full width at half maximum. And so on our thing here, here's the maximum. And so then we're talking about the full width at half maximum. And that's a good spectroscopic term to know. For those in the back, can you see that a little better? So full width at half maximum. Knowing that, you should be able to figure out half width at half maximum. In this particular formula, though, it's just called delta lambda. So that delta lambda in this formula is the full width at half maximum. We have all 3 parts of our line shape formula. I mean, we have the Boltzmann piece here. We We have the absorption profile from the transition dipole moment integral here, and then we have the line shape formula, which is this big piece here. G stands for Gaussian in our case, so it requires a full width at half maximum, this delta lambda piece. It requires the different transitions, so the wavelengths for the transitions that you've got from the transition equation, because it's going to put a peak on every one of those. And then it's going to be a function of wavelength. So this is that formula. This 4 and natural log of 2, those kinds of things convert that delta lambda from sigma to full width at half maximum. So those are in there just so that the Gaussian function works with spectroscopic terms. Okay? And then we have this. This is the actual wavelength of the spectrum. And this is the wavelength of the transition. So on the board, this would be the wavelength of the orange light. And then we're sitting at red, so that would be the wavelength of the red. That's not going to make sense unless you're in class today. Okay. So we're sitting at the red wavelength, and the L end to end prime, lambda end to end prime is right here. And so this would be calculating that intensity right there. And then if we move a little further over, L changes and we get a different intensity. We move over, finally we get to L equals L end to end prime, and we get that intensity. Okay. Also, these are 3 things that you need for every peak. Like how do you describe a peak? You need the peak height, you need the peak center, and you need the peak width. If you give me those things, I could sketch it out. Right? I need to know how wide it is, I need to know where it's located, and I need to know how tall it is. The line width is related to the resolution of the instrument, or whether the molecule is being hit by collisions or traveling really quickly. So there's a lot of physical things in that line width that can cause it to spread out. But most of the time, and here's the thing to pay attention to, most of the time that line width is just governed by our instrument. So you'll hear me talk about instrumental line width. You have to get a really high resolution instrument to measure the Doppler effect. And that molecule running towards the light, that's the Doppler effect. Okay? You really have to have a high resolution system to measure collisional broadening, because it doesn't change the molecule's absorption profile very much at all. It doesn't spread it out much. And then if you get down to the uncertainty, like Heisenberg's uncertainty principle related to the location of the difference in those energy levels, then you get to the Lorentzian line shape, which is next. So the Gaussian line shape would be just the most common. It'd be the instrumental line shape. We would use this most of the time. Just for instrumental line shapes, use a Gaussian. Okay, so that's one of your questions on the homework. When would you use the Gaussian line shape? Just to model instrumental line shapes. Here we are, you're looking at the Lorentzian line shape. So this is a different shape. Look at the green curve. I'm going to go back and forth, and we can compare the Gaussian to the Lorentzian. Look at the Gaussian. There's Gaussian. That's Lorentzian. Same height, same center, same width, different shape. Gaussian, Lorentzian. Gaussian, yeah, Lorentzian. So Lorentzian in the middle looks skinnier, but then down at the bottom it doesn't taper off as fast. So it's just a different shape. It's a different function. Yes?
Is that still approaching 0 on both sides?
Yes, yes. I just had picked the window for the Gaussian, and then when I plotted the Lorentzian, it went off scale. And I was like, I don't want to redo everything. But it does eventually go to 0. But you see it doesn't go to 0 very fast. It tails off. And the Lorentzian, you can also, so the Gaussian, what was the other name for Gaussian? Normal. The other name for Gaussian line shape was the normal line shape, or the normal distribution. Okay, Lorentzian has another name for it as well, and it could be confusing, so everybody wake up. Okay, the other name for the Lorentzian is the natural line shape. Natural. Yeah. Okay. Because it's related to nature. The Lorentzian line shape is that Heisenberg uncertainty principle, the result or ramifications of being a little uncertain as to the location of those energy levels. Uncertainty related to Planck's constant over 2 pi. Okay, so that uncertainty relationship tells us we don't exactly know where those energy levels are, but if we had a super high resolution spectrometer, it would not go to 0. Okay, the width of this peak has a natural limit, and the natural limit for the location of this orange transition is the Lorentzian line shape. So you would almost never use this one, but I put it in the notes so that you would have at least heard of it. And when people talk about the natural line shape or the Heisenberg uncertainty line shape or the smallest possible line shape, it would be the Lorentzian line shape. What happens when you get kind of close? Like it's kind of half due to instrument and half due to nature, right? Because it's not a switch, right? You don't get a better and better spectrometer and all of a sudden, boom, it's all Lorentzian. It might be half of the line shape being from your instrument and half being from the natural line shape of the transition. Well, you just do a weighted average. So the Voigt profile, the Voigt line shape, is just a weighted average. So like 30% instrument and 70% natural. And so what's the weighted average piece? That's just this little A here. A and 1 minus A. So this would be really an ugly, an ugly thing to look at. Okay, because you've got A times the Lorentzian piece and then 1 minus A times the Gaussian piece. And to put that in Excel, no. I've not even done that. That's just forget about it. It's too ugly. Okay. All right. But if you had a spectrometer that was approaching the natural wavelength or natural line shape, then before you got there, you'd have to use a Voigt profile to model the shapes of your peaks. And then lastly, if we're in visible spectroscopy, a lot of times underneath those peaks, you have hundreds or thousands of other transitions. You've got the vibrational transitions, and then you have the rotational transitions, and they're not symmetric. So if I've got my orange wavelength, I might have more rotational transitions on the long wavelength side than I have on the short wavelength side, or vice versa. So I may have an asymmetric peak. Notice what we have so far is everything's symmetric. What do I mean by symmetric? Well, look at the center of that peak. It's the same on both sides. And what if in reality, in a real spectrum, I have an asymmetric peak? It tails to the right or tails to the left. We need to have a line shape that tails. And so this would be a log normal line shape. So we had to add another parameter. We had to add an asymmetry parameter. And that's that rho there, the Greek character rho. So again, don't try to copy that formula down. It's pretty ugly. But you've got logs inside of logs with squares, and it's just crazy. Now, thinking about all of these log terms, you've got, you've got a log of rho in the denominator, and so you better not take the log of 1, right? Because then you got 0 in the denominator, and 0 squared is still 0. So if you pick 1 for your asymmetry parameter, it blows up, and you get an error, okay? But you can do 0.99999, and that's fine, okay? It's just a tiny little number in the denominator. But if you pick 1 for your asymmetry parameter, try to model a perfectly symmetric peak with the log normal function, you're going to get an error, okay? So you didn't do anything wrong if that happens, okay? Just change your asymmetry parameter to where it's close to 1. But nice, look at this. So you see it's really steep on this side and tails off on that side. And so that asymmetry parameter where we're talking about lambda high and the lambda transition. So this is the lambda for the transition here. And then wherever this full width at half maximum drops down, that's lambda high. And where this end of the full width at half maximum drops down, that's lambda low. And so the asymmetry parameter is just this this distance here divided by this distance. So it's just a symmetry parameter, right? It's how offset is that full width at half maximum. So you can see now there were lots of options for line shapes, but Excel already has the normal distribution function in it. All you have to do is type in norm.dist and open parenthesis, and you put the wavelength you're sitting on, the center wavelength for that transition, the width of that transition, and then true or false, telling it either to make the distribution curve or the cumulative distribution, which I forget which one. I think you just say false, and it gives you the distribution function. So it gives you a nice Gaussian peak centered on lambda n to n prime, and with the width of the full width at half maximum. Okay. And so that's what we do for this. We take that full width of half maximum, that spectral line width. We have the stick height. We have the center of the peak. And then we have the wavelength values for the spectrum. So that's the wavelength axis for our spectrum. And we compute this shape for every one of our transitions. And so this is called spectral convolution. Write that down. Spectral convolution. C-O-N-V-O-L-U-T-I-O-N. Convolution. It's actually up there on the slide now, up in the top left corner. Spectral convolution. Okay, and this is the last slide. We take every peak has its own Gaussian. So we calculate the line shape for every transition. And then as we're scanning this light through our cuvette, we might have at this point a contribution from this transition and another one and another one. And so each wavelength is the sum of all of the contributions all the way across the spectrum. You see that? So at each wavelength, we have the sum of every contribution of every peak that can happen in our cuvette. And that gives us our final result, simulated spectrum.
And the Gaussian is that curve going down.
Yes, this is the Gaussian here. And you see one for every transition. And then if we're sitting at this wavelength here, we get the contribution of that one, plus that one, plus that one, plus that one, and it gives us that spot right there. So that's what's going on in your total spectrum. Under every spot in that spectrum, you might have 50, 100, 200, or 1,000 transitions. And what does that mean? Well, there might be a million molecules in this state that absorb, and 200 in that state, and 5 that absorb there. So since you have so many molecules, statistically, everything's happening. Every transition at that wavelength, as long as the intensity is substantial, can absorb. You don't really have a contribution from this one right here, way over here, or from this one over here, way over here. But you still have about 5 or 6 that are contributing to that intensity. Okay. And so that's spectral simulation, and you guys are doing it. This is fantastic. Okay. So enjoy this week.